All right, guys, welcome to Unit 5 Quiz 2 Study Guide. Let's go ahead and go over this and see if we can help you guys get ready for your quiz next week. All right, so it says, find the relative extrema of the function and explain your answer. Now, how this question is going to be graded is you get 2 points for finding the critical values with your work shown, and you get 2 points for correctly identifying the relative extrema with your work shown. Altogether, this question is going to make up about 23% of your test. This is one of the bigger questions on your test, or your quiz, I should say. All right. So, now I'm just going to go through it with the steps that I taught you guys with, but you can also, I'm going to point out at the end where the points you're going to get actually lie. So even though I'm going to follow the steps, I'm just doing this so it's not unfamiliar to you, but really you only have to show certain parts of this, and I'll show you what they are, okay? So the first thing that I would encourage you guys to do is to make sure that you identify any discontinuities, because if there's any discontinuities, then those do not qualify as relative extrema. You can't have a relative extrema if there's no point there. Okay, now since this is a polynomial, there are none. So we're good to go. We can move on from that. Number 2, you want to find your critical values. All right. So to do that, we need to find our derivative, which is 3x squared minus 4x. And then we go ahead and we do 2 things. We're going to set the derivative equal to 0, and we're also going to look and see where the derivative is undefined. Now, since this derivative is also a polynomial, it has no places where it's undefined, so I'm not going to get any critical values from this one. And just so you guys know, we did look at a variety of functions with these types of questions, and some have different things going on. Some are pretty tough because the derivative is harder or the algebra is harder, but on this particular quiz, I'm just going to be giving you guys polynomials, so you can take a little breath of fresh air there. It makes it a little bit easier. Next, you're going to set your derivative equal to 0, and you're going to solve it to see if you could find any critical values that way. On this one, you can factor out an x, and if you set each factor equal to 0 and solve, you get x equals 0 for one of them, and for the other one, you're going to get 4/3. Okay. The next thing you're going to do now depends on how you want to do it. You could do either the first derivative test or you could do the second derivative test. It doesn't matter. Both of those methods will work at this point. We've talked about 2 different ways to find relative extrema, the first derivative test and the second derivative test. Now, since this is a polynomial, polynomials work really well with the second derivative test, but based on this quiz, I know the questions that are coming up, and it might help us a little bit to go ahead and just stick with the first derivative test in this case, just because I know the questions that are coming up after this ask us questions about the slope. So looking at the first derivative test will be easier on this particular quiz, but usually, yes, I would totally encourage you to go with second derivative test in this case, but we're going to go ahead and go with first derivative this time. Okay. So for the first derivative test, what we do is we make a number line. We put our critical values on that number line. Smallest one on the left, bigger one on the right. Infinities on the ends. And that gives us 3 intervals that we need to test. And we want to know what's going on with those slopes in those particular intervals. So we're going to plug a number in from each interval into our first derivative, and I'm going to do this a lot today, I think, because I've been doing it a lot lately. I keep putting f, but our function's not named f, it's named y, so if I forget again, just be aware that was a mistake. But so a number that's between negative infinity and 0 would be -1. A number that's between 0 and 4/3 would be 1. and a number that's between 4/3 and infinity would be 2. All right, and so I want to plug those in to my first derivative. So if I plug those into my first derivative, I get 3 plus 4, which is 7. And that means that on the interval from negative infinity to 0, my graph is going in an upward direction because it's a positive slope. Next, y prime of 1. So I'm going to plug in a positive 1 this time. So if I plug in a positive 1, I get 3 minus 4, which is negative 1. That's a negative slope. So from 0 to 4/3, we have a negative slope. And then for the last interval there, from 4/3 up into infinity, I'm going to be plugging in 2. If you plug in 2, we're going to get, let me do some mental math here. 2 squared is 4, times 3 is 12, minus 8 is 4. So I get 4, which is another positive slope. Okay? Now, as you guys can see, if you think of this as a curve, this point would be a relative max, and this point would be a relative min. So, for this point here, 0, we have a relative max. Oh, did it again. And then for the other point, we have a relative min. Okay. Now, just so you guys know, on an FRQ test, on the AP exam, they do not give credit for this as an explanation. I don't know why, but they don't consider number line tests to be a good way to explain your work. I'm going to go ahead and count it for myself, just because I'm just not going to emphasize that too much right now, but just do be aware that the number line test does not count as an explanation if they ever ask for an explanation. An explanation, which we'll see later on in this quiz study guide, is that the reason this is a relative max is because y prime goes from positive to negative at that point. That's how you would say it. But they, for some reason, and I don't know why, they do not count a number line test as a good enough explanation. But for our quiz, that's probably not a big deal. So let's talk about how I'm going to be grading you on here, okay? You get 2 points. You get 1 point for having the correct answer, but you can't get that point unless you also show your work for how you got that answer. In this case, you don't need to write that. I can assume you can realize that in your mind, and you don't need to write this either, because once again, I can assume you would realize that in your mind. So you get 1 point for showing the work, and if you show your work and you get the correct answer, you'll get that 2nd point as well. For number 3, if you show your work correctly, you get 1, and if out of that comes the correct answer, you get another point, for a total of 4 points, which is 23% of this quiz. It's estimated percentages because it's going to be out of 17 points approximately, but there you have it. All right, let's go ahead and move on to the next question here. On what intervals is that function increasing? Now that's number 2. But I'm going to answer number 3 at the same time. Now, in your guys' actual quiz, I'm only going to ask one of these questions. I'm not going to ask both, and it's only going to be worth 1 point, which is about 6% of the quiz score. Okay? So, but on this study guide, I'm going to go ahead and just do both. So, on what interval is the function increasing? Well, I'm going to bring back really quick the work that I just did. And we could see that this interval here is increasing. So from negative infinity to 0, my function is increasing because it's going up. And also on the interval from 4/3 to infinity, it's increasing because it's going in an upward direction. And it's between, I forgot to highlight this, and it's between 0 and 4/3 that the function is going in a downward direction. It's decreasing. Okay, so that's what we need. Now, I'm not going to ask for any explanations on number 2 because, once again, you've already shown the work for it in the beginning, so you don't need to provide an explanation. Now, if you decided to do the second derivative test on number 1, then you wouldn't know that yet. So you would have to show some work to get the credit for it. But in this case, I can assume your work is already in part 1. So what we saw was that it was increasing on the interval from negative infinity up to, was it 0? And it was also increasing on the interval from 4/3 to infinity. And it was decreasing on the interval from 0 to 4/3. All right. And that's all I'm going to do is I'm just going to ask you guys to put the interval or intervals. It's a 1-point question. You either get it right or you don't. And that makes up about 6% of your test. I'm going to assume that you showed your work in step 1 because you already did the first derivative test. So no need to show any extra work there. All right, let's go ahead and take a look at number 4. On number 4, I'm asking you, on what interval is the function concave up? All right. Well, to do this, we need to look at our second derivative. Okay, so let's remember what the original function was really quick. The original function was that, and so the first derivative was that. But when you're talking about concavity, then you really want to be looking at the second derivative, which would be that. Now, how can we find where the concavity is at? Well, first of all, let's find where it equals 0, and we're going to do a number line test for that. And I'll show you how to work that out really quick and how that gives us our answer. So we're going to set that equal to 0. We're going to solve. If you add 4 and divide by 6, you're going to end up with 4/6, which is 2/3. Now, I'm going to make a number line for my second derivative. All right. So for your second derivative line test, you're going to be plugging in a test point from your interval into the second derivative. So what's a number less than 2/3? Well, 0 is always really convenient to use, so let's do that. And let's plug in a number greater than 2/3, like 1, for instance. So now if you plug 0 into your second derivative, you're going to get -4 as an outcome, which means that if your second derivative is negative, then that means that on that interval, the graph would be concave down. If you plug in 1 to your second derivative, you're going to get a +2, which means that on that interval, it's concave up. So we can now answer the questions here for 4 and 5. Now, once again, I'm not going to ask the question twice. I asked one question, where's it concave up, where's it concave down, but I'm only going to ask one on your quiz, and it's going to have, it's actually going to be worth 2 points, because I'm going to assume that you did the first derivative test on number 1, and so you haven't gotten to the second derivative yet. So I would want you to show your work on this one. But anyway, it's concave up on the interval where the second derivative is positive, which is this interval from 2/3 to infinity. And it is concave down on the interval from -infinity to 2/3. Because the second derivative was negative. Okay, so how is this one going to be graded on your test? I would want to see your work that you did. That would be 1 point. And if you showed your work appropriately and you got the right answer, you get another point. And so that one's going to be worth 2 points. On my thing here, it said 1 point, but I'm going to adjust that. It's supposed to say 2 points. And so that one's actually going to be worth 12% of your grade. All right, let's go ahead and move on, and we'll take a look at number 6. Where are the points of inflection? Well, actually, we can answer that question based on what we just did. A point of inflection is a place where the derivative is either equal to 0 or undefined, and 2/3 is a place where our second derivative was equal to 0. So 2/3 is a possibility, but the function has to be continuous at that point, which it is because it's a polynomial, and also it has to change curvature at that point, which it does. It goes from concave down to concave up at that point. So we have our answer for that one already by the work that we did on that particular problem. And so there is a point of inflection at the point x equals 2/3. And that would be fine. I don't care, I guess based on the way that I've worded it here, if I ask for a point, maybe we should write it as a point. You don't actually need to plug it into the original function. You can just put y of 2/3. That would be fine with me. Okay? And that's worth 1 point, which is 6% of your test. And once again, I'm going to assume that if you did the ones above it, numbers 4 and 5, if you did those already, then you've pretty much already shown the work, and you don't really need to give any more explanation. So the only thing you really have to do is give me the point, and you'll be good to go. That's worth 6% of your test. All right, numbers 7 through 12, I'm not going to be going over these. I just wanted to give you some extra practice if you wanted it, and you can look at the answer key to see if you got them right. It's just extra practice, and that's it. So on your actual quiz, I'm not going to give you a whole other set like this. It'll just be one set like this. Okay. So let's go ahead and move on to a new question here. So before we begin number 13, I want to take a moment to compare and contrast numbers 13 and numbers 14. On number 13, I'm giving you a graph of a derivative, whereas on number 14, I'm giving you the graph of a normal function. And so the interpretation of these graphs will therefore be different. So for instance, if I give you guys this, that's this spot right here where x equals -2. And the output looks like it's a little bit more than 3, so I would guess that to be like maybe 3.5. And what I want you guys to understand is that this is my x and this is my y value. Now over here on this graph though, if I pick a point on my graph, like let's say f prime equals 3, that's going to be like right here, and that equals 5. But the interpretation is different. Okay? This is an x value, but this number here, although it's a y value on this graph, it's also the answer for the derivative at 3. So this is the slope of f at that point. Okay? So these are different interpretations because this is a graph of the derivative on the left and a graph of a standard function on the right. Okay, so that is an important thing to understand. Okay, now you could call this the y value of the derivative, but the y value of the derivative is the slope of the original function. Okay. So that being said, let's go ahead and get started here. So the graph below is of the derivative f prime. Identify the intervals of increase and the intervals of decrease of f. So I'm giving you a graph of f prime, but my question is about f. All right? So once again, this is going to be worth 1 point for correctly identifying the intervals, and it'll only make up 6% of your quiz once again. You don't have to provide an explanation. You can just give me the intervals. I'm going to write my explanation out, but you don't have to. You just need the intervals. So I want to know, where is f increasing, and I want to know, where is f decreasing. Now, f is increasing anytime its slope is positive, or in other words, the derivative is greater than 0. Now, since this is a graph of the graph of the derivative can be found to be greater than 0 anytime the derivative is above the x-axis. So, for instance, from here to here, all those points will give me a derivative value of positive because they're above the x-axis. And also from here to here. And so the intervals where the derivative is greater than 0 are from negative infinity up to negative 2, as well as from 2 up to infinity. Okay? From negative infinity up to negative 2, and then from 2 up to infinity. Right? Now, where is f decreasing? F is decreasing anytime its slope is negative. In other words, when the derivative is less than 0. And since this is a graph of the derivative, I can find where the derivative is less than 0 by looking for where it's below the x-axis, and that would be here, in between negative 2 and 2. So the interval where the derivative will give me negative values is from negative 2 to 2. Now, you don't need to include these explanations. I think those are great to have. I wouldn't hate it if you did it, but you only need to have the intervals that I ask for. Now, on your quiz, I don't recall, I may or may not ask for both. I may just ask for where it's increasing, or I may just ask where it's decreasing. But doesn't matter. So long as you put the correct answer, you get the 1 point that that question is worth. Right? Now we're going to switch our thinking a little bit, because now I'm looking at I'm not looking at a graph of a derivative. I'm looking at the graph of a regular function. Okay? And so when that's the case, like I told you, the answer for this one will be a y value. But the derivative, as you guys know, that'll be a slope, right? But since I'm looking at a graph of the regular function here, we're going to, how will you know what the slope is at any given point? Well, we know that if the original graph g is going in an upward direction, then that means that my derivative is greater than 0. If it's moving in a downward direction, that would mean that my derivative is less than 0. And if I have a flat tangent line, that's where my derivative would be equal to 0. Okay? Now, backing up a little bit, we could talk about how you know when g is positive, negative, and 0. Let's see if I can move this really quick. No, we'll move that one. All right. So I'll put it up here. So anytime when you're looking at this thing here, anytime the dot is above the x-axis, then that would mean that g is greater than 0. Anytime the dot is below the x-axis, that would mean g, the y value, is less than 0. And anytime g is on the x-axis, that means that g equals 0. Okay? And then finally, if this is a graph of g, then what does g double prime represent? Well, that represents the concavity. So if you have a function that is concave up, that would indicate that g double prime is greater than 0. If you have a graph that's concave down, that would indicate that G double prime is less than 0. And if you're looking at a specific point where the graph changes from being one form of concavity to another form of concavity, I don't like that picture. That works, but I'll put one that's maybe a little bit more normal looking. So maybe like it goes from being concave down to being concave up. That point where those two concavity things switch off, that's what we call a point of inflection, right? And that's what happens anytime G double prime equals 0. Okay, so for each of these problems, now on your quiz, just so you know, I'm only going to have one set like this. I'm not going to do a whole bunch of them like I have here on the study guide. I'm just giving you a variety of questions so that you can kind of see a bunch of different outcomes. But let's go ahead and we'll see how this works here. It says, let me read the directions real quick. The graph of G is given below. For each point indicated on the graph, we're going to complete the blank with a symbol that is less than, greater than, or equal to. You're only going to receive one set like this, and it's worth 1 point if you get all 3 correct, and it makes up 6% of the test once again, or the 6% of the quiz, I should say. All right, so the first thing we're going to do is we're going to identify the x value. It's negative 1.5. So you're going to want to find where that is at on your graph. That's right here. Now, the first thing is, this should actually say G. All of these should say G. So I'll have to go back and change that later. But for now, this is just the regular G, which is the graph that we're looking at. So that's a y value. So since that dot is above the x-axis, the y value there would be about 1, right? Which means that it's greater than 0. That's the y value at that point. The y value of G at negative 1.5 is greater than 0 because it's about 1. Now the next thing it's asking for is the slope. Now look at this line here at this point that we're considering right now. Both before and after it, it's going down. That's a negative slope. So that means G prime of negative 1.5 would be less than 0. All right, and then finally, at that point, we want to know what's going on with the second derivative. Well, I would say that our graph is concave down from here to here, and I would say that it's concave up from here to here, which means that this point right here in the middle is a point of inflection. And whenever you have a point of inflection, the second derivative is equal to 0. So I would say this one equals 0. Okay? So basically you want to know, is the y value above, below, or at the x-axis? Is the slope positive, negative, or equal to 0? Is it concave up or concave down? That's how we're going to handle all of the questions that are coming up here. All right, let's go ahead and take a look at part B really quick. And once again, I will change these before I upload it, but these are all supposed to be G's. All right, so now let's do G of 1. So once again, we're going to start by finding our x value on the graph, 1, and that's right here. At that point, what's the y value? The y value is about negative 1, right? So G of 1 is negative 1, which means that it's less than 0. This is my slope. Now at that point, to the left of my dot, it's going down, but to the right, it's going up. And that's because the slope at that point is a flat slope, which is 0. And so that one's going to be equal to equal to 0, because the slope was going from decreasing to increasing, which means that it reached a slope of 0 right at that point. So anytime you can draw a flat horizontal tangent line, that would indicate that your slope is 0 at that point. Now I want to do concavity, and we had that up there earlier. We said that from here to here was concave down, and we said that from here to here was concave up. And as you can see here clearly, the dot is in the pink area. So since it's concave up, we would say that the second derivative is greater than 0. All right. So I'm going to be erasing these because I'm out of board space at this time. But, well, maybe I could scroll it down a little bit. We'll see what it looks like. Let me try to keep it up there a little longer because I do have a few more I want to go through. There we go. That'll work out fine. Okay, let's go ahead and take a look at C now. Cover up A real quick, and B. All right, so for A, we want to find the x value of -4. -4 would be right here. At that point, my y value is below the x-axis, so I would say that g of -4 is less than 0. This is to the left and to the right, it's going up, so that's a positive slope there. And my second derivative, that's on the part of the graph that's concave down. And so for that one, my second derivative would be less than 0 because it's concave down. Finally, we have over here one more to look at. We're going to look at -2. All right, so -2 is right here. And at that point, my y value is above the x-axis, which means that it's greater than 0. My slope, that would be another horizontal tangent line, so that would be equal to 0. And the concavity, that point is on the interval that was concave down, so that's less than 0. So you guys will have one question like that, and it's all three of them make 1 point. All right, number 15, we'll come back to that one in a second. But I'll read the directions. You're going to use a table that's provided on question 4 of the 2005 FRQ. You can either Google it to look at the table, or you can find the table on page 164 of the blue book, which you hopefully have picked up by now. This one is worth a lot of your test. I'm going to ask you to tell me certain things based on that table, and you should also be able to give me a reason for those things. For a total of 5 points, and that one takes up a bunch of the points on the test. But before I do that, because I'll have to change slides to get to that one, let's go ahead and do number 16 here real quick. So for each problem, not problem, but problem, misspelled that, below, determine if f of -2 is a relative min, max, neither, or not enough info. You get 1 point for finding the correct answer. All right, so for part A, the y value of the function is left 2 and up 7. It's not the y value, I'm sorry, that's the point. Left 2, up 7. The y value is 7. The x value is -2. So that's the point. We have a 0 slope, so I'm going to draw a dotted horizontal tangent line there to represent that. And then my second derivative is negative, which means that I have a concave down graph at that point. Now, if that's the case, then this would have to be a relative max. All right, let's go ahead and take a look at part B. So basically, just turn it into a picture. -2, 8 would be here. Slope is 0 again, but this time my second derivative is positive, so now it's concave up, which means it would have to look like that. And that, therefore, at that point, -2, or f of -2 would have to be a relative minimum. All right. So you don't have to graph it. I mean, you could tell based on the fact that the point exists, the slope is 0, and the concavity is down. That all those things put together make for the answer that we have. But if it helps to graph, you can. Now, for this next one, we have a point at -2, -2. I have a slope of 0. But my second derivative is 0, which is inconclusive. Anytime your second derivative is 0, then it's inconclusive. And what that means is not enough info. It may be a relative min, it may be a relative max, it may be neither. We just don't know. That's not enough information. All right, let's look at the last one. So we have -2, +3. My slope is 5, so I can't draw a flat line this time. A slope of 5 is positive, so I would have a slope moving up in that direction there. And my concavity is positive, so I would have a graph that maybe would look something like this. But that's not a relative min or a max. In order to be a relative min or a max, this would either have to be undefined or 0, and it's not. It's 5. The slope is 5. But in order for a relative min or a max to exist, you have to have a slope that is either 0 or undefined. So this one is definitely neither. Okay? So there is a difference between saying neither and not enough info. Not enough info means that maybe it is a relative min, we just don't know. Neither means it's definitely neither one of those things. Okay? So anytime you have zeros, you're either going to get an answer or an I don't know. But if this is not a 0 here, then the answer is definitely neither. All right. Now we can jump over and do this FRQ on number 15. Okay, so let's go ahead and read our instructions first to kind of wrap our mind around the problem. F is a function that is continuous. In other words, there's no holes, gaps, or jumps. And we're looking at this interval. Now that's kind of significant because that means that the 0 is included in the interval, but the 4 is not. So we have an open dot. It stops at 4, and it does not include 4. The function f is twice differentiable except at x equals -2. That means that the derivative exists everywhere except at x equals 2, and the second derivative also fails to. Well, the second derivative also exists everywhere except at -2. Okay. The function f and its derivatives have their properties indicated in the table above, and D and E means that it doesn't exist. Okay, so I think we're ready to begin here. Now, on this particular question, in order to get the point for each one of these, you have to give the answer and the explanation. Okay? Now, critical values. Critical values are those places where the derivative, I'm going to show this off on the side because this is just for teaching, and then I'll write my final answer the way you should in a moment. Critical values are those values where the derivative is either equal to 0 or it's undefined. Or you could say does not exist is fine as well. So looking at our table, let's find, oh, and by the way, they're x values also. That's important. It's the x values where the derivative does not exist or is equal to 0. So let's look at our derivative row here. I see a 0 here. I see it does not exist here. And the x values that go with those are 1 and 2. So I would say x equals 1 and x equals 2 are critical values since f prime of 1 equals 0 and f prime of 2 does not exist. Okay, that's it. So you can't just tell me 1 and 2. If you do that, you'll be losing some credit. You have to include the explanation that shows me that you understand why those are critical values. All right, let's go ahead and take a look at number 2. We want to find a relative max. Now there's two ways to find a relative max. One is with the first derivative test. The other is with the second derivative test. So let's kind of talk about those really quick here. So for the first derivative test, it's when the slope
f prime changes from positive to negative. In other words, your graph changes from going in an upward direction to going in a downward direction. That's one way it could happen. It could also happen with a sharp turn like that. So that point at the top of each of those would be a relative max. Okay, so you're going from a positive slope to a negative slope in either case, positive to negative. And that would be your first derivative test. So where on our chart does it seem like the slope is changing from positive to negative? Positive, positive, 0, positive, does not exist, negative. Oh, there's a change right there. So we're changing from positive to negative right here at x equals 2. Okay, now the question here is asking us to find the relative maximum. Well, that would be the y value. So the y value at that point is 2. So you could say there's a few ways you could write it. I think I'll just stick with I'll just write all three, and it doesn't really matter. We just have to be careful. It doesn't really say whether it wants the x value, whether it wants a point, or whether it wants a y value. So I'll just show you the different ways that you could say this. Here we go. So here's our answer. The point 2, 2, or you could say at x equals 2, or you could say y equals 2, is a relative max since f prime changes from positive to negative at that point. That would be fine. I don't really like this one a whole lot, honestly, because y could equal 2 in a few different places, but I think let's just go ahead and write the point. It doesn't matter. I'll give you credit either way, but I think maybe the safest thing to do is put just the point or to put x equals 2. Anyway, sorry to be so flip-floppy on that. So that's one of our solutions. Now, another way, and that's the only place, I don't really see it changing from positive to negative anywhere else. Now, another way to find a relative extrema is with the second derivative test. That's where you find all the places where f prime equals 0. And actually, it could also be where f is undefined, or f prime, I mean. So let's see, we have that here and here. And if at that point f double prime is negative, that's another way to find a relative max, because that would mean that you have an upside down curve with a flat spot at the top. The double prime negative, what makes it upside down, the prime equal to 0 or undefined is what makes it flat on the top. And the reason why it could be undefined is if you have a cusp, because at that point, well, that's not really concave down. Let me redraw it, but you could have something that looks something like this, for instance. And that would be like a sharp turn all of a sudden. And at that point, you don't really have a slope at that point because there's a cusp, but it is still changing concavity to a defined point. So whether it's 0 or undefined, so long as f double prime is negative at that point, then you're good to go. Anyway, rambling on. But as you can see, neither one of these have a negative second derivative, so we can't really come to any conclusions there. So we'll leave that one off. Now to continue, so this is our only answer then for number 3. For number 3, you're going to do the same thing. It's just that all this stuff is the opposite.
So when you're looking for a relative minimum, which is number 3, we're looking for something that either looks like this, or we're looking for something that looks like this. All right, and in either case, we would, well, in this case, we would need a derivative that was equal to 0. And in this case, we would need a derivative that was undefined or didn't exist. But on both cases, to the left, it would need to have a decreasing slope. And to the right, it would have to have an increasing slope. Okay, now, let's start by looking for where the derivative equals 0. We're back to these same 2 points again. But we've already established that both of those were relative maxes. And therefore, we've exhausted all of our possibilities here. So there are none. And your explanation would be there are no points for which the derivative equals 0 or is undefined, and at the same time goes from negative to positive. So we don't have any places where the derivative is 0 or undefined and at the same time goes from negative to positive, which is the requirements for having a relative minimum. So there are no relative minima. So my answer would be none, and my explanation would be there, right there, that entire sentence. All right, let's go ahead and talk about points of inflection. All right, in order for a point to be a point of inflection, a couple of things need to happen. First of all, the second derivative either needs to equal 0 or not exist. Second of all, it needs to be continuous. And then third of all, the concavity needs to be changing. So let's start with the beginning there. Are there any places where the second derivative is equal to 0 or does not exist? Well, there's one right here. And there's also one right here. And there's also one right here. There's 3 places. That's done. Are they all continuous? Yes, they're all continuous. The problem tells us at the very beginning that f is continuous on the entire interval. And you can also tell it's continuous at those points because they actually give you coordinates for those points. If it wasn't continuous, then you wouldn't have a y value at that spot. So yes, all 3 of them are continuous. Now the last thing we need to do is we just need to make sure is the concavity changing at those points. So in other words, we either need to go from concave up to concave down in order for that point to be a point of inflection, or we need to go from concave down to concave up in order for that point to be a point of inflection. So we have to look at the second derivative, and it has to change from positive to negative or negative to positive at that point. So let's take a look at our first possibility here, the x equals 0. And let's look to the left and right. Does the concavity change? Yes. So that's a point of inflection. The concavity goes from negative to positive. Let's look at the next one. Does not exist at x equals 2. Does the concavity change there? On the left it's positive, on the right it's negative. It sure does. So once again, we have another point of inflection. Finally, for our last possible choice, does the concavity change there? It does. So all 3 of these points here, where the second derivative is 0 or does not exist, meet the criteria. The second derivative is either 0 or does not exist, it's continuous, and the concavity changes. So all 3 of those points are points of inflection. So the first point would be 1, 0. The second point would be 2, 2. And the third point would be 3, 0. Since the second derivative equals 0 or does not exist and changes signs at that point. Now you don't have to say it's continuous, and the reason you don't have to do that is because they say it in the directions, so we're okay with that. But there you guys have it. So here's the answer, and here's the explanation. You need to state that and that in your explanation. All right, so those are points of inflection. All right, so for number 5, the last thing we're going to do is we're going to sketch the graph of this function. Now, we went over this in class, and basically what you're going to do is you're going to start with this row by plotting points, because those are just the y values for each x value. So at x equals 0, y equals -1. So I've got a dot right there. And at x equals 1, I've got a y value of 0. And at x equals 2, I have a y value of 2. And at x equals 3, I have a y value of 0. And remember what we said about 4? Because we do need to go from 3 to 4. We said that that was an open dot, and they don't give us the y value. So I don't know where to put that dot just yet, but we'll figure out a good estimate of that in a minute. But just remember, it's going to be an open dot. All right, so let's begin. After you plot your points, you're going to go through and you're going to do all the slopes then. And I would just make some straight lines. So at the first point, my slope is a positive 4. So at that point, I'm going to make a slight little positive line there. Positive slope, I should say. And then between 0 and 1, it stays positive, so keeps going up. But by the time you get to 1, the slope is 0. So now I'm going to draw a flat slope. And then between 1 and 2, it's positive again. At 2, it doesn't exist, so I can't draw anything there. At between 2 and 3, we've got a negative slope. And then at 3, we still have a negative slope. And then between 3 and 4, we have a negative slope. And there's no telling how far down to go. They didn't give us enough information. But I do know that I plan on stopping at 4, so I'm going to maybe cut that off like right about here. And I'm going to put an open dot. Okay, it doesn't matter where you put that dot because they didn't tell you where it should go. Okay, so that's good enough. Now that's kind of what the graph looks like, but now we want to go through and put one more final touch on it. We want to get the concavity right. So at 0, it's concave down, and it stays concave down until you get here, and then it's concave up after that. So whenever you get to x equals 1, it stops being concave down. So we're concave down all the way to here, and by the time we get to x equals 1, then it switches and becomes concave up. So concave down, how would I connect this dot to this dot, which is where x equals 1, with concave down but still sloping upwards? It would have to look like that. So I'm going to slightly bend my line so it goes in that way. And we want to make sure we keep that flat slope at that point. But after that, between 1 and 2, now we have a positive second derivative, which means that it should be concave up. So from here to here, I'm going to make it concave up. So I want to put a slight bend in it. So maybe I can back up a little bit and try to do this a little more smoothly. There we go. All right, next at the D and E, nothing happens, but at between 2 and 3, we have a negative second derivative, which means it's concave down. So as I connect this dot to this dot, it's got to be concave down. And sure enough, there's that cusp that I thought would have been there at the beginning. So there's our concave down. And then at 3, we should have a 0 slope, or sorry, a 0, which means that it's a point of inflection. So it's changing from concave down to concave up. So from here to here, it's going to be like that. There we go. And so I'd say that green line is the final touch. So the first thing you want to do, just go through, plot your points. Next, just using straight lines, sketch some slopes. Final touch, put the curves on there. And then you have your final answer there. And we have an open dot at this endpoint here, and a closed dot at this endpoint here. And so the green line represents the final solution there. All right, and that pretty much does it. So hopefully that was helpful to you guys, and we'll see you guys in class next time.